You remember fiber Bragg grating? So if we just simply modulate refractive index of fiber core with some period, we'll have a structure which is reflecting some certain range of the wavelength. So it can be a mirror, and in fact it will be dichroic mirror. It will be high reflective for this design wavelength, for example 164 nanometers, and it will be transparent for other wavelengths, especially the pumping wavelength for example 975 nanometer. Yeah, so we'll have a mirror from this side. We can put another Bragg grating from this side. Yeah, with of course the same wavelength 164, and partial reflecting. It can be, for example, 50% reflection and 50% will be transmitted through our mirror, and it will form a resonator between these two mirrors. So we'll have this resonator, we'll have active media, so we'll have a laser. In the case of fiber lasers, the gain of active fiber typically is extremely high. It can be 30 dB or something like that. So sometimes even leaving this end of the fiber just cut perpendicularly can be enough to ensure this first 4% of the reflection from such a structure. It will be enough to form a laser resonator. So it can be also like that. And typical picture showing you the idea, we are using pump combiner. This type of a coupler I showed you on the previous lecture, just to connect couple fibers into one cladding of our double clad fiber. Then we have double clad fiber, active fiber. Of course, all these fibers need to be double clad, and in some piece of this fiber we have this Bragg grating written on the core of a fiber. So we have a mirror, we have some pigtail as an output of a laser, and here we can have this surface of this perpendicularly cut fiber, just to have this 4% of the back reflection, enough to excite generation of the light in such a structure, in such a fiber laser. Here you have some data for, let's say, more practical solution. Once again, you can see a name of a company I mentioned to you on this previous lecture. These are the leaders in the fiber lasers market. You can see also what is possible for their approach to making such a lasers. Of course, it is CW laser, so continuous wave. Output powers from 8 kilowatts up to 120 kilowatts output power. Yeah, fiber core diameter, here you have quite high numbers, because the output from this certain laser is in multimode fiber. The powers of this order are so high that they cannot be propagating in single mode fiber, because this 8 kilowatts is way above damage threshold for single mode fiber designed for 1 micron wavelength. Yeah, so it isn't possible to have such a high power in single mode fiber. There are ways how you can increase this threshold and other things, but generally, if you have so high power laser, you need to use multimode fibers. So the output beam, it isn't nice Gaussian beam, but it is multimode beam, so the quality of such a beam, it isn't so nice, but it can be enough for some applications, especially this extremely high power 120 kilowatts of output power of the laser is extreme power. In fact, even though the core diameter is 300 microns, the power density you can achieve from such a source can be extreme, and it can be used, for example, for some what is the name? Same like fiber splicing, but not the splicing is in that case. Melting metals, at least, yeah. This power allows you to just cut metals and also to connect them using this melting process. An example, how such a system can look like. The number tells you about the power, the output power of such a laser. So this is 20 kilowatts laser, 30 kilowatts. You can see it isn't a big box. Another thing is cooling for such a laser, because typically they are water cooled, so you need to additionally add some cooling system to this laser. But you can see how high powers are available for fiber lasers, and typically they are, as I told you, CW lasers, because for CW laser, fiber laser, it is quite easy to have this CW operation. The resonator is pretty simple because we are using only some kind of fiber mirrors. It can be Bragg grating, it can be also a cut of a fiber. You can easily pump such a structure using these power combiners, and using proper dopants, for example ytterbium, the efficiency of such a fiber lasers, it can be extremely high. Yeah. Unfortunately, for the applications where we want to have some pulsing operation, making such an approach using fiber laser approach requires to use also some modulator, for example, inside of the laser resonator. Yeah, you know this Q-switched fiber laser you measured on the laboratory. So you know, inside of the laser we need to put some modulator. Since the power isn't big, for low power applications it is good approach, but for high power applications you cannot put any fiber modulator inside of the resonator because of these powers which can appear in such a fiber laser, especially inside of the resonator. Yeah, especially inside of the resonator, the power can be extreme, and in fact the pulse peaks for such lasers are very limited, and for pulsed laser, peak power is the key factor, key parameter. So we want to have as high peak power as possible for such a lasers. So it will be difficult to have such a peak power for fiber laser. Another thing connected with the length of such a resonator, typically it is at least couple meters. Making short pulses in Q-switching technique is impossible. Something close to 100 nanoseconds is typical pulse duration for such a lasers. You have such a result also on the laboratory. On the other hand, classical solid-state lasers, they have pulse duration couple nanoseconds. So you can imagine the shorter pulse is, the better you will have peak power, for example, having the same energy in a pulse. So regarding this pulse duration, this approach of making standard lasers, standard fiber lasers with high power, it isn't practical. Yeah, so fiber lasers, high power fiber lasers, are limited mostly to these CW fiber lasers, and they can be used as a CW laser even for pumping other fiber laser or fiber amplifier. IPG is making also some structures with fiber lasers pumped by other fiber lasers, which are pumped by semiconductor lasers. Yeah, they have also such approach for making fiber lasers. So there is a possibility, especially in this fiber technique, but not only in fiber technique, that there is used another approach. You know, the gain of this active fiber is very high. Yeah, so this is the first thing important if you want to change the approach of making the high power radiation of the fiber. We can easily build a laser, low power laser, which has a lot of different parameters controlled. For example, wavelength, polarization, pulse shape, pulse duration, and other things you can set quite easily if you have low power laser. So you can pulse it, you can force it to just mode locking operation, you can have some Q switching laser, low power laser. Yeah, so in the low power regime, it is extremely easy to have the properties of the radiation. In fact, anything you want, you can have. In fact, regarding these wavelength polarizations and other parameters of the radiation, but not the power of this radiation. So the approach can be as follows: we can just have low power laser and then amplify the radiation of such a low power laser in the amplifiers. Optical amplifiers, typically a chain of optical amplifiers, because if we are starting from, let's say, 1 milliwatt of optical power and we want to have 1 kilowatt, so we need to have 1 million the gain of such a structure, and having 60 dB of a gain in one amplifier is impossible. Yeah, so this is why typically we are using a cascade of the amplifiers to achieve such a powers. And this is so-called MOPA configuration, master oscillator power amplifier. Yeah, master oscillator. This is the some low power laser which has all the parameters we want to have, but not the power. And then we are amplifying such a low power radiation to desired power level using some amplifiers, and the last stage, power amplifier, which gives us this required power level. Yeah, what can be this laser, this master oscillator? They are called also SIT lasers. Yeah, SIT. This is the name which appears in this MOPA configuration very often, because it is the laser which just defines all the parameters of the radiation, but not the power. Yeah, so they can be semiconductor lasers, they can be fiber lasers, also solid state lasers, especially if we want to have application with very narrow line width of the lasers. So semiconductor or fiber lasers aren't able to have extremely low, extremely narrow lines. So in such a case, you can use solid state laser. For other applications, typically we are using semiconductor lasers, or for some of them also fiber lasers are good SIT lasers for such a structure, such a approach. And here you can have an example of such a MOPA configuration. At first, in this classical approach, because this paper was presented before the era of these fiber power combiners able to withstand high optical powers. You can see pumping power for this laser was up to 500 watts. Yeah, so you can imagine all the components need to be designed for such a high power. So this first approach was made using fiber technique up to the last stage, and the last stage of this amplifier is made in this bulk optic techniques, because it was just for beating a record. Yeah, it was a record on the days it was published, 150 watts at third telecommunication window at 1.5 micron wavelength. Yeah, but right now it is possible also in fiber technique, also extremely high gain, and the chain of the amplifiers, allowing to reach high power on the output. Some data of the fibers I'm using in my applications, it was a couple years ago. Typically, such a double clad fiber, this is erbium ytterbium co-dope fiber. The parameters: core diameter close to single mode core of single mode fiber. First cladding of such a fiber 125 micrometers. And absorptions, for the pumping wavelength, absorption also for the wavelength with the highest attenuation in such a fiber. Numerical aperture of the core and first clad numerical aperture. It is also important parameter regarding this pumping. How many semiconductor lasers you can connect to such an active fiber. First clad shape, octagonal. I told you why we aren't using this, let's say, circular geometry of such a fiber. We are using typically this first clad with, let's say, octagonal shape. It is just for mixing all the pumping modes to force them crossing the core of our fiber to take part in the pumping of this core. Otherwise, in this circular symmetry, there are some rays which can just avoid crossing a core, and they are wasted regarding this let's say pumping of our active fiber. And you can see also a green radiation coming off the fiber. It is because of this excited state absorption of erbium ions. We are exciting erbium ions to upper state using 2 photons of pump radiation. So as a result, we'll have some green radiation on the output. Other component for such a power amplifier, this fiber combiner, typically it looks more or less like this. Quite a small device, able to have 2 watts per pumping input and 10 watts of pumping input, and also 10 watts can be propagated through this output fiber. You can see a geometry of the fibers. It is tapered bundled fiber coupler. So you can see a geometry. This, let's say, input geometry. Something somewhere here. You can see 6 external fibers. These are multi-mode fibers. And these are inputs for the pumping lasers. So these are multi-mode fiber with 105 microns core diameter. And inside there is a single mode fiber matching to SMF28 fiber. So all the dimensions of this fiber, they are exactly the same like for single mode SMF28 fiber. And after tapering of such a structure, you can see all the fibers melted together. The diameter of this structure is matching to this double clad fiber, which is on the output of this combiner. So from input side we have these 6 multi-mode fibers and 1 single mode in the middle. On the output we have this double clad fiber, which is just spliced to this structure, to our fibers, which are tapered to this certain diameter to match exactly the outside external diameter of our double clad fiber. This is how such fiber combiners are made. Another component, typical component, pumping laser, and example of the 10 watt semiconductor laser operating at the wavelength which are able to pump erbium ytterbium co-doped fibers. Of course, the parameters of this output fiber are exactly matching this combiner parameters, and some results for such a structure. It was pumped by with two 10 watts lasers, so maximum pumping power was 20 watt in fact, but our measurement just ends at 16 watts of pumping power. This is the output power. You can see not so high, but in fact on the laboratory, where you are measuring this erbium doped fiber amplifier, on the black black on the black breadboard, you have also on this table, there is this amplifier pumped with only one pump, and it is also exercise for the students. Yeah, and the gain spectra is close to 1550 nanometer wavelength, so third telecommunication window. In the fibers which are co-doped with ytterbium ions, there is sometimes a problem with this amplified spontaneous emission emitted by also ytterbium. Yeah, we want to have erbium emission and erbium gain, but unfortunately also ytterbium, which is just additional component in these fibers. Also ytterbium emits some noise, so this ytterbium noise sometimes it is limiting factor, especially for let's say old erbium co-doped fiber. It was right now they avoid this problem by some technological improvement to such a fibers, and right now the active fibers for this third telecommunication window, I mean these active double cut fibers, they have no issues connected with this noise for such a, for ytterbium ions. Yeah, so this is the solution for, let's say, some low or middle power amplifiers or MOPA systems. Yeah, so if you want to have couple watts of couple tens of watts of power, you can use this approach. If you want to add another stage of these amplifiers, we need to avoid having high power density in the core of a fiber. Yeah, since this one has 7 micron core diameter, so you can imagine if you have some pulses in inside of such a fiber, this pulse peak will be extremely high, so also this power density will be extremely high. So the way how we can avoid this problem and how we can increase the maximum peak power of such a systems is to use fibers with higher core diameter. These are so-called large mode area fibers. Yeah, this is the name of this kind of fibers. You can see, for example, here fibers which has core diameter 20 micrometers or 25 micrometers. So you can imagine if we just simply expand the core size, we'll have couple mode fiber. To maintain a fiber to be single mode, you need to remind this formula for this condition. If the fiber is single mode or multi-mode fiber, yeah, this normalized frequency for the fiber, you can see if we are increasing the diameter of a core, we need to decrease the numerical aperture of the fiber, and then the fiber can still be single mode fiber. Yeah, if this V number is smaller than 2.405, it means the fiber is single mode fiber. Yeah, so this is why you can see the numerical aperture of a core is much lower than for standard single mode fiber. For single mode fiber, it is 0.17. Yeah, the numerical aperture. Here it is 2 times less, so it allows to just maintain this single mode operation for such a fiber. Yeah, if you just extend the core diameter even more, unfortunately, making a fiber which has extremely low numerical aperture isn't so easy. So for higher core diameter, other solutions need to be taken to maintain a fiber be a single mode. For example, if all fiber is banded, bending losses for the fibers is dependent on the mode number. For this zero order mode, bending losses in such a fiber, they are the smallest in comparison to other modes. So if you have a fiber which is able to propagate up to, let's say, the second order mode,
yes to anybody.
just simply bend it.
Like the time when you and I got married.
And it will just
I'm not helping.
remain
So you
to
said
be
yes
a single
to him,
mode.
and you just
if you are
had
bending such a
our
fiber,
baby.
yes,
That
but
is right.
unfortunately,
And
this bending
traditionally,
gradients
the daddy is supposed to give the mommy a present, but I am prepared to let that
single mode
go.
operation, they are pretty small, so it isn't so practical solution. So later on, I will show you another way how we can increase a power of one single laser. Not only fiber lasers, but in fiber lasers also it is very popular solution to increasing the power of fiber laser above limits for one single fiber laser, because the limits are strictly connected with this high power density in such a in a core of a fiber. Yeah, we cannot exceed some certain power, not damaging the fiber or not exciting some nonlinear effects which are preventing us to having the power we want to have. For example, to have 100 kilowatts of output power and having hold the output beam in single mode fiber. It isn't possible in classical approach. Some examples of third stage: almost nothing different than the, let's say, second stage of such a MOPA system. The only difference is since we are using this LMA fiber, this large mode area, we need to just match a mode field of the single mode fiber with this mode field of this large mode area fiber, and typically it is made by so-called mode field adapter, which is just simply some tapering of the fiber, yes, to just smoothly go from higher core diameter into lower core diameter. So if you just simply take such a double clad fiber, put it to the fiber splicer, turn on the discharge between the electrodes, and then start to pull, you will can make such a taper on such a fiber. Yeah, so you can control, of course, the ratio of this tapering and then cut a fiber in a place where you have some certain diameters matching this single mode fiber. This allows to just transform the beam from single mode fiber into large mode area fiber with as small losses as possible. Of course, there will be losses, but this approach can minimize losses on such a connection. Otherwise, if you just simply splice such a single mode fiber to LMA fiber, you will have huge mismatch of these mode fields and also mismatch in the numerical aperture. So the losses of such a connection, such a splice, they will be quite big. Couple dBs can be a losses for just simple splice of such a fiber. So this is why we need to use also this mode field adapters. Yeah. Oh, this is the picture from Fiber Splicer showing you how it can be done. Yeah, this is the picture from this Fetal splicer. I showed you a splicing process on second lecture with these fibers. So the picture looks quite familiar, and here you can see different diameters of a fiber. So also you can see a core which is bigger here than here. Yeah, so this is this LMA fiber which was tapered, cut at some certain diameter, and here is the splicing between single mode fiber and this LMA fiber after tapering, of course. And some results: up to 40 watts of output power for this LMA fiber with only 140 watts of pumping power. So it is the result I had a couple years ago here in this laboratory. And this power is enough, for example, to, let's say, melt a brick. If you just simply use a lens to focus the light from such a laser into a brick, you will melt it and make some glass layer on the surface of this brick. So this brick will be heated to a couple thousands of degrees, yeah, to just be melted. Yeah, so these are the applications also, not melting a brick, but it can be used to have some micro machining or other thing. In fact, this laser you were operating in this laboratory in first round, it was also fiber laser in this MOPA configuration. So it was low power pulsed laser and then fiber amplifier to the power of 20 watts. If you want amplify extremely short pulses, because it is good approach for amplifying let's say nanosecond pulses, but you know already there are lasers which can have picosecond or even femtosecond pulse duration. So mode-locked lasers are emitting such a pulses, and for such a pulses using single and simple fiber amplifier, it isn't enough, because for such a short pulses this peak power is so extreme that we can damage a fiber by this pulse which is amplifying in this active fiber. Yeah, so here you have the schematic. We are amplifying a pulse in the fiber amplifier, and at some distance we are exceeding this threshold, this damage threshold for the fibers. They can be exceed quite fast. I mean, for even small average power of such a pulses, we can exceed this threshold for maximum peak power of the pulse. So completely different approach must be taken to gain such a short pulses. This approach is called CPA technique. CPA means chirped pulse amplification. This is the technique which can be used for amplifying femtosecond laser pulses. At first, we have extremely short pulse. So we cannot just put such a short pulse to the fiber amplifier, because we will just exceed this pulse peak limitations for such a fiber. So at first we are decreasing the peak power of such a pulse just by simply stretching it in some dispersive media. I hope you remember chromatic dispersion. Chromatic dispersion just broadens the pulse in time domain, changing the pulse into, let's say, some time domain rainbow. Yeah, femtosecond pulses, they have quite wide spectra, so it is relatively easy to stretch them using just simple fiber. Yeah, if you just simply put femtosecond pulses into the fiber which has big dispersion, it will be stretched in this way. Then we are amplifying such a pulses in our fiber amplifier, and after, on the output of such amplifier, of course using bulk optics, because it cannot be done in a fiber, we are compressing them back using some element which has dispersion exactly negative, exactly opposite to this dispersion of the stretcher. Yeah, so we will compress our pulse. Yeah, here you can see the blue wavelength are traveling faster through the stretcher than the red wavelength. So compressor need to be designed to have exactly opposite dispersion. It means the red wavelength, the longer wavelength, need to travel faster in this compressor than shorter wavelength. Yeah, so if you match the dispersion of a stretcher to the compressor, after this compression you will have exactly the same pulse duration, but much higher peak power. Because in this amplifier we are amplifying pulse energy. Of course, pulse peak is also amplified, but since the pulse is stretched for certain energy, the pulse peak will be much smaller than after compression. Yeah, even though the energy of the pulse for after amplifier and after compressor, they can be more or less the same, the pulse peak for after compressor will be much higher. And this method was invented by Gerard Moreau and Donna Strickland. Donna Strickland was she was his PhD students, and this method, this approach to amplify high peak power pulses, extremely short pulses, it was worth to have a Nobel Prize in physics in 2018. Yeah, so they just get this Nobel Prize for this method of the pulse amplification. It is so-called chilled pulse amplification, and this is the method how we can amplify extremely short pulses in not only in the fiber amplifiers, because also in bulk optics amplifiers. For example, in ELI laboratories in Prague, they are operating with extremely short pulses with extremely high energies, so they want to reach petawatts of peak power for such a pulses. So they are using not fiber optics, but they are using bulk optics amplifiers. And also for such a high light intensities, this bulk optics needs to utilize this CPA method for amplifying extremely short pulses. Yeah, and some example from our laboratory, of course, it can be done also here, but with slightly lower power levels. And you can see typical configuration. We have some seed laser. Of course, it is also MOPA system, so we have seed laser. This was a fiber laser with just mode-locked fiber laser. Then dispersive fiber, one amplifier, then second amplifier, somewhere between pulse peaker, just to decrease the frequency of the pulses, because repetition rate for this laser was 40 megahertz, and we want to have much lower repetition rate. So it means we have a train of the pulses, and we need to cut only every nth pulse from this train. Then the second amplifier, and finally power stage. You can see LMA fiber, even though the powers wasn't high, but since we are operating with these extremely short pulses, they had so high peak power that we need to use this LMA fiber as a gain media for this last stage. And after amplification, yeah, the stretcher was here, this dispersive fiber, so it just simply acts like a stretcher. After gaining, we have pulse compressor. Typically, these compressors are basing on diffractive gratings. In certain configuration, they will give you some certain dispersion of this output beam. Changing the distances of these gratings in this compressor, you can change the dispersion of such a compressor. So results, you can see this, let's say, output peak here, 1 picosecond of the pulse duration. The input pulse duration was, I don't remember, was of course slightly lower. It was below 1 picosecond, but in real life, of course, you cannot compress ideally to the same length of the pulse like you had from your, let's say, seed laser, yeah, because some nonlinear effects also are broadening the pulse, and it cannot be compensated by, let's say, dispersion, this dispersive element. So sometimes the pulse after compression is slightly longer than before this CPA system, but you can see a pulse energy and peak power on the output of the laser. So you can see peak power is way above megawatt. of this power. While average power of such a pulse is quite small, 2 watts of output power, you can think it is nothing, but regarding such a high, extremely high peak power, even this 2 watt of the energy are able to make some marking on the materials and other things, and since the pulses are extremely short, we have no heating effect in this machining at all. Yeah, so this is the most important application of such a lasers, because if you are machining some material, these thermal effects are quite important if you want to have extremely good quality of your surfaces here and edges of these, let's say, channels cut in some materials and other things. So this is why short pulses lasers are also important. And this was a result published somewhere. Okay, so regarding the MOPA systems, it is all for today. And last part of our lecture, because next week we will have this test. On the last part, I will show you what can we do if we want to have power much higher than able to produce a laser, one single laser with such a high power, because we have limits, yeah? You know, limits for this Gaussian beam on the output of the laser. For fiber lasers, this limit is quite low, below 10 kilowatts of output power. So what can we do if we want to have much more power on the output of our laser, and you want to have still good beam quality? So this is scaling of the high power lasers, and typically it is made in so-called beam combining technique. So you can imagine we will have couple beams and we'll combine them together to have higher power, and coherent beam combining. Why it must be coherent, you will get known in a moment. Yeah, some application of such a high power lasers, heavy industry applications, have high power lasers, also science, yeah, exploring high energy physics, for example, in this laboratory of extreme light infrastructure in Czech Republic. These early laboratories, they are also using such an approach. Long distance free space optocommunications, especially regarding this inner satellite optocommunications. Between satellites we have optical links, and you know there is no possibility to have free space propagating beam without divergence. Yeah, so after some certain distance, and we are speaking about thousands of kilometers distance between the satellites, the beam received by the receiver will be extremely small. So we need to also use some high power light sources to such applications. And the mostly developed beam combining technique is for military applications, laser weapons. Yeah, laser weapons, this is the, let's say, main field of developing for such a beam combining systems. So more or less you know already the limits for single emitter sources. Yeah, beam quality degradation for high power lasers, these thermal effects and other things. For fiber lasers, of course, we have these physical limits for the maximum power density in the gain media. Yeah, single mode fiber, as I told you, 10 kilowatts of output power from single mode fiber. This is the damage threshold for such a single mode fiber. Also limits for the shaping and guiding optics. Yeah, you can imagine if we want to just direct a beam to a target and the beam is quite small, because typical aperture of the laser is pretty small. So the damage threshold for the mirror for some lenses also is important factor regarding extreme high power lasers. So how we can avoid these limits, how we can scale up our lasers, I think this is the best picture showing you what we should do. In fact, you can see George Lucas invented these beam combining methods, because it is quite more or less obvious. Just add a couple laser beam together and you will have more power. So this is simple laser beam combining solution. But if we want to have some, let's say, gain, adding beams together, we need to make it in such a way to maintain a beam quality. And to maintain a beam quality, we need to make this beam combining in some, let's say, coherent way. Coherent means keeping all the beams we are combining in coherence to each other. Two examples of such a combining. We have two beams and they are overlapping on a target. What will happen if these two beams aren't coherent to each other? Of course, we'll have some light intensity from the one beam and we'll have some light intensity from the second beam. So they will add together and that's all. So the intensity in this central point will be as twice one beam intensity. The shape of it will be maintaining the shape of one beam, and that's all. But if we overlap two beams but synchronize in phase to each other, and the angle between the beams will be small, they will interfere, of course, on this target area, and they will form some interference fringes pattern here. So the light intensity will be, here I can draw you the envelope for, let's say, these two beams added incoherently, but for coherently added beams we'll have something like that. I will show you better picture in a moment. So in the central part, we'll have not doubled intensity of one single beam, but it will be intensity to the square. It will be 4 times higher than one single beam intensity, because here we will have some dark spots, because of interference. The same can be done using some beam splitting optics. If we just simply take a beam splitter, which is 50 to 50 beam splitting, it means we are putting one beam, it is divided to 50% to let's say, pass our beam splitter, and 50% is transmitted after reflection. So you can imagine if we just add second beam from this side, it will be also divided by a half. So as a result, we will have 100% power here and 100% power here. So no gain at all. But if we keep some phase relation between these two beams constant, we can adjust phases in such a way to have one beam going through the beam splitter and second beam to be reflected. So as a result, we will have 200% of one single beam power. Both of them will go here and nothing, zero power will have in this arm. But we need to keep some phase difference, some constant phase difference between these two beams. In such a case, it should be 180 degrees, pi radians degrees. So this beam should have, for example, 0 radians, and this should be 180 degrees of phase shift versus this beam, let's say, horizontal beam. And then all the power will be directed here. If we just change this phase difference in this way, yeah, having 180 here and 0 degrees here, all the power will be transmitted to this one. And of course, the power will be doubled versus the one beam. So we can use two approaches, two geometrical approaches, overlapping beams or combining them on some beam combining optics. And they can be different approaches using beam splitters, also using diffractive gratings. Quite typical approach to combine high power laser beams in coherent way. If we don't keep the beams coherent here, we'll have all order of diffraction appearing on the output of our structure. If we just keep phase relations between these three beams, like on this schematic, constant, and of course it needs to be some certain phase relation between the beams, we can overlap them in such a way, and other diffraction orders will disappear. So we can have all the power in one single beam as a result. Yeah, so this is so-called field aperture beam combining, because we are adding beams, overlapping them one onto another using some beam combining optics. But there is another approach similar to this approach I showed you on this previous slide, overlapping beams together at some longer distance. Typically, it is made in such a way. We are producing parallel beams using, for example, some fibers and lenses to produce some parallel beams. So in the cross section, the output beam of such a structure looks like that, yeah, in the so-called near field. So right after the output of such a structure, yeah. So looking from this side, it will be, let's say, 9 fiber collimators. But in so-called far field, in the case of incoherent combination, I mean, all the phases, all the frequencies of these beams are completely independent to each other. We will have something like that. Yeah, we will have a beam which has, of course, some intensity, but the diameter of this resulting beam will be exactly the same like a diameter of a beam of one single emitter. Yeah, due to divergence of such a beam. If we keep the relations between these beams constant, in fact, they need to have exactly the same phase, yeah? So they need to be matched in phase. The phase of these beams need to be controlled and keep constant. As a result, in so-called far field, we'll have such a picture: one central lobe with the intensity equal more or less to the intensity of one single beam multiplied by n square. Yeah, so we have huge gain because such a beam diameter here in this focal, let's say, far field pattern will be more or less the same like we have one single beam but with high aperture emitted from the laser source. Yeah, so these are the combining schemes. I mean, these geometrical schemes. We can also combine a beam in incoherent way. Space domain I showed you previously. WDM multiplexing, because we can overlap a beam with different wavelengths. Polarization beam combining also can be done, not coherently, but we will have no gains in comparison to this coherent beam combining. And couple examples of such incoherent beam combination, very often used for semiconductor lasers. Every laser emits slightly different wavelengths, and they are combining together on some diffractive grating. Depending on the wavelength, of course, the angle of diffraction will be slightly different, so we can combine all the beams together into one fiber. Or fiber combiner, I showed you on the previous lecture, also can be treated as something which just combines beams incoherently, yeah? Because we don't care about the phases. We are only putting a beam from one multimode fiber into multimode fiber with higher core diameter or higher numerical aperture, that's all. There is also a possibility to have beam combining using laser phase synchronization, and typically it is made quite simply, building couple laser resonator but with, for example, output coupler common for all the lasers. Yeah, so for this laser, for example, the resonator is formed here. For this laser, it will be formed as follows. This laser will have such a resonator, and this one will have such a resonator. So if you just made something like that, in a natural way, all the lasers will synchronize to each other just to form a resonator and to keep the phase differences between them constant to avoid wasting energy in this laser resonator to these other arms of these beam splitters. The same, of course, will appear if you use this diffractive grating and put output coupler, output mirror of the laser resonator here. Yeah, so it will be quite natural that all the lasers will start to operate, and all the beam here will be emitted only to this output coupler, and almost nothing will be directed to these orders of diffraction. Other examples, because it can be also done with this fiber lasers approach, so we can just build parallel fiber lasers and force them to be in synchronism in phase, for example, yeah, to just form one common beam on the output side. But unfortunately, all these approaches, they need to have one common element, for example, output coupler for such a construction, such a lasers. So output coupler will be the limit of the output power of such a approach. So it isn't so good, but yeah, exploring the limits and exploring the limits for such a structure, it was made for fiber lasers, showed that randomity of such a structures is so high that you cannot maintain a stable operation of such a thing, and scaling with the pumping power and with the amount of the synchronized lasers, it isn't so good and very hard to control. So in fact, right now this approach was left alone, because there is much better way how to make this beam combining in coherent way, yeah? Because we want to just add beams together coherently. You know, this MOPA configuration, we are using seeding laser, cascade of the amplifiers, and after some certain output power, we will just hit a limit for one single emitter. So what we can do on the next step of our power scaling, just add some splitter of the signal, and on the last stage, just simply use parallel amplifiers. Yeah, so every amplifier, of course, will have this limit for this output power, but since we will have, for example, 5 or 10 parallel channels, in combination of all output power, it can be much higher. The only thing we need to maintain will be the phase of these output beams to keep all of them in synchronize, because other parameters, they will be coherent to each other by default, by design, because we have one light source. Yeah, all the waves which are going out from every channel here, they are exactly the same waves coming from exactly the same source. So the only thing important here will be a phase difference between these amplifiers. Going back to our beam combining geometry for a while, here are, let's say, more real results which can be for such structures. And here you can see typical shape for output beam in near field and far field, not drawn on let's say PowerPoint, but as a result of some simulations. Yeah, far field pattern. You can see this central lobe is much higher intensity than these side lobes, which can be barely visible here. And couple examples of such a systems. At first, field aperture approach, we are using polarization beam combiners and parallel amplifiers here, combined the 4 in this case, yeah, combining the beams in polarization, but it is coherent combining because we are controlling also the polarization state, changing the phase difference between these two beams, so just to hit the proper polarization in the next stage of the combinations and other things. So this can be this is approach with this field aperture method. You can see efficiency of such a combining. It can be quite high, 96%. Yeah, so only 4% of the power is lost in this setup. Beam quality can be high. M² less than 1.1. It is not. It is good beam quality, almost Gaussian beam. Another example. This one is using this polarization grating as a diffractive grating as a beam combining element. So it is also field aperture combination system. These are 3 lasers. Every laser has 1 kilowatt of output power, and 3 of them just gave 2.4 kilowatts of output power in the beam, which has quality M² equal to 1.2. Also quite nice beam quality, also quite close to this Gaussian beam profile. And you can see near field beam profile and far field. As you can see, no signs of higher order modes here visible. Yeah, only the shape was slightly elliptic, I guess. So this is why this M² is not so good, because 1.2 it isn't Gaussian, but close enough to be a Gaussian beam. All these field aperture methods of beam combining, they have unfortunately one huge big disadvantage. This disadvantage is connected with this element and other elements. We will hit a limit connected with the power density on these elements combining a beams, and of course these mirrors which are used for directing a beams. So for the highest power applications, especially for these military applications, this tilt aperture approach is much more useful. And here you have some results, some data for different arrays, and the data from some experiment, some simulations. Here you have also, here you can compare, for example, the amount of the emitters, how it influences on the far field pattern. You can see for one aperture we'll have such a beam, 7 apertures packed close to each other. Of course, it is important. They are giving quite high central lobe, but the side lobes are still visible, so they have quite high energy in them. So just to improve this factor, the best solution is to just simply use more emitters, array of 19 emitters. You can see in the same scale this central lobe is smaller than for this case, and also the side lobes are barely visible here on this picture. Another factor connected with this tilt aperture settings is so-called fill factor. Yeah, we can have different collimators. typically collimator has this Gaussian beam on the output of the collimator, not covering the full aperture of such a collimator. So you can see a resulting far field patterns for such different fill factors of the beams. Yeah, this C column here, these are collimators which has the output beam almost covering all aperture of this output collimator, and you can see this central lobe is the most intense one. These side lobes are smaller than for this case, and in comparison this one is even worse. And far field pattern from such a fill factor if you have non-coherent beam combined. Yeah, so this is exactly the same scale. This is near field pattern, so right after the collimators, and this is the far field pattern. It means somewhere in the infinity. And this infinity, this far field typically is made in laboratory, of course, because in real life we'll go at some kilometer distance. So in such a distance, the beams are overlapping. In laboratory, we are making this far field artificially using a lens. If we have these parallel beams, they are meeting somewhere, and they are meeting in this artificial infinity point. So the far field pattern is recorded exactly in the focal spot of such a lens. What will happen if we just have a fill factor remaining but changing the spacing? You can also see what will be the result. Yeah, if we are changing the distance between the emitters, we are making these lobes to be smaller, but the fill factor for such a structure will be much worse. So we'll have a lot of side lobes here visible. So this central lobe don't carry enough energy. And here you have some, let's say, real data taken by me. Two different fill factors for such a matrix. It was 4 collimators in some orthogonal placement, yeah, and for let's say commercially available collimators, this output beam was small in the center of the collimator, so as a result this far field pattern looks more or less like this. But later I was just made a collimator by myself, having almost 100% of the fill factor, and this allows to have much better efficiency of such a beam combining. Yeah, so this is result showing you a huge difference between this thing. I have some movies with this operation of such a system. Maybe they will work. Yeah. Without synchronization of the phase between beams, you can see the whole picture is flowing. After starting up the synchronization between beams, you can see the whole picture is steady, stable. Unfortunately, I didn't record a movie for this, let's say, improved version with these collimators made by myself and much higher fill factor, but the operation is more or less the same. You can imagine only cutting the central point will give you more or less the same result, and this central peak will be much higher than these side peaks here. Yeah, if I just shot two collimators, yeah, so if I just simply remove two collimators, it was in horizontal. Right now it is vertical removal. Yeah, so for two collimators operation, of course, we have only just this interference fringes. This was by diagonal shutting the collimators. What else do I have here? This kind of systems, they can be scaled quite nicely, increasing the number of parallel channels. Yeah, and we are closing to the end of the lecture, so maybe I will give you only yeah, I will skip a couple slides here, showing you and telling you only something about this, how to have these beams synchronized in phase. And of course, classical approach of such a synchronization is to just sample all the output beams, yeah, interfere them with some reference beam and detect a signal, yeah, to just have some reference beam with some constant phase. We are comparing the phases from every channel with this reference beam and detecting a signal, telling us the phase of this one single emitter, and then we are controlling the phases of all emitters to have exactly the same phase. But it is extremely complicated from optical point of view. Also, all the electronics is pretty complicated. So there is another possibility. We can also use approach using only one photodetector. Yeah? Instead of having every channel independently controlled in phase and controlling a phase and measuring a phase of each channel independently, we can use a photodetector, one single photodetector, for measuring a phase of whole total combination. I mean, measuring the effect of all the combination. If we just simply will look in this far field pattern on the central part of it, we can control all the channels in a way to maximize this signal. Yeah, you can see. In the case of in-phase, synchronization between the beams will have some maximum value. If they will be in out of phases, we'll have some lower value, depending on the phases relations between the channels. Yeah, so we are just sampling central part of such a far field pattern, and we can just simply control a phase in order to maximize the output signal. It can be done in different approaches. One of them is so-called frequency tagging, because maximizing the signal if we are somewhere on a slope, we want to have information if we are on such a slope or this one. Yeah, so we are adding additional modulation to the phase signal, modulating a signal, and as a result we will have in phase or out of phase response depending on the slope we are on. And of course, if we are on the top of such a maximalization, we'll have no signal at this certain frequency. So using just ordinary phase detector allows us to build such a system in so-called frequency tagging method, or Americans who invented this method, they name it also log set. And this is quite common approach for the systems which are designed for the American army, but there is another possibility using some, let's say, artificial intelligence algorithm, stochastic parallel gradient descent. This is the method which is quite simple and quite efficient for such applications. We are just simply adding slight phase shift to the channel, and then we are observing if the output power just increased or decreased. If it increased, we are keeping this change and going randomly to another channel, trying to make exactly the same. So we are slightly moving next channel by some phase change, very small phase change, and we are observing the result. And we are continuously going randomly through all the channels. It is important also to make it randomly. As a result, after some certain amount of the iteration, all the channels, they will be in synchronized, and we will be somewhere on the top of this function. You can see, unfortunately, the time of this convergence is pretty dependent on the amount of the channels. So for huge amount of the channels, it can be quite slow process. But let's say for typical values of the channels, it is quite useful, and it can be applied, and it is quite commonly used for such a systems. And to, let's say, summarize our lecture, because we are out of time in 2 minutes, a couple examples of the log set, for example, approach. You can see it can be also done for field aperture scheme of the operation. So because we have this diffractive element to combine 5 fiber lasers together. Some results for this one, you can see every channel has m square less than 1.1 and m square for the combination of such a channels. Do I have somewhere the result of m square for this combination? Unfortunately not. But it was something close to 1.1, maybe 1.2 or 1.3. And you can see combining efficiency equal to 82% in one single beam, with the quality quite similar to the beam quality of one single amplifier. Yeah, so you can see we have huge gain just simply adding 5 beams together. Yeah, this one can be skipped because I want to show you at the end huge advantage of tilt aperture beam combining, because tilt aperture beam combining, I showed you previously. Yeah, we having these parallel beams. We having this lens which are forming this artificial far field, and we are trying to maximize a power here. But in real systems, of course, we don't use such a lens. We have a beam which are transmitted through the air, and after couple kilometers they are overlapping, and there is a target after this couple kilometers distance. But since the beams are propagating in atmosphere, which is turbulent typically, yeah, everybody who just observed some distant object, but during some hot day, for example, and especially if you are trying to make it on some, let's say, road with some dark surface, you will see the picture of these distant objects. They are fluctuating, flowing, and they aren't steady for sure. And of course, the same will happen with the laser beam, which is propagating. Yeah, so after some propagation through the atmosphere, the beam will be completely degraded. Yeah, so even though at the emitter you have a Gaussian beam, after some distance, the beam quality will be extremely poor, fluctuating, and the diameter of this beam, it will be changing all the time. But using this tilt aperture method, we can observe not somewhere close to our emitter, but we can observe and try to maximize beam intensity on the target. Yeah, so this is so-called target in the loop configuration, and this allows us to just simply compensate, at least slightly, atmospheric turbulences. Yeah, increasing the beam quality, just controlling the phases of these emitters, not to have the same phase on the output, but to meet in phase on the target. Yeah, and such a system can look like this. This is, let's say, holy grail of such a systems. You can see these emitters. Yeah, so here is 3x7 emitters, so 21 emitters. We have some telescope just to observe a target, and the signal for this photodetector is taken from this signal observed by this telescope. Additional optics. These are some range finders for the application that they were using, and the results showing with and without using this atmospheric compensation. Maybe not on this slide, but I have a movie, so I will show you. Here you have different pictures showing you a result. What is possible with and without this target in the loop configuration. So this is, let's say, typical far field pattern if we don't have any atmosphere. Yeah, so we are artificially creating this far field pattern, and here you have examples of the output beam. What is possible with and without this target in the loop configuration. Yeah, so depending on these fluctuations and how it looks, I mean these two beams with and without, I will show you the end of this slide. Yeah. Here you have a beam which isn't synchronized in this configuration, compensating the atmosphere, and here is the same power of the beam but using this target in the loop configuration. Yeah, so you can see the intensity of this beam is much bigger than the intensity of the beam on the left. In fact, the diameter of such a beam is much bigger than the screen you were observing a beam. So this is why the intensity of this beam is much smaller. Okay, so we finally reached the end of a lecture, so we can finish for today. And of course, we will meet on the test next week. You are asking me what will be the format of the lecture test. The format will be as follows. I will prepare you a forms on ePortal, but you will have no questions and no answers on this form, because the questions and answers, possible answers, they will appear for you on Zoom. I will just start a presentation with the questions for you and answers. Yeah, so it means you need to be parallelly on the Zoom, and after knowing the answer, you need to put this answer to the form on this portal. Yeah, so you will have a form only to mark these answers to the questions. Regarding a lecture, I think something close to 40 questions that they will be this lecture part. Every question will have 4 answers possible. Of course, only one will be correct. And for the laboratory part, because after having this, let's say, fiber part, we'll have this laboratory part. Questions are single choice. Yeah, so only one answer is correct. The others are wrong. And for the laboratory, I think something close to 3 questions per exercise they will be, so it will give 36 questions. Do you have other questions? At first, I will answer regarding this question to about the test. How much time? Something close to 40 seconds or 45 maybe per question. this will be a time for every question. Yeah, so they will appear, of course, and there will be no possibility to go back to the question. So you will have a sentence of the questions, and you need to answer one after another without leaving questions for some later marking, because it will be just sequential test without any possibility to go back to the previous questions.
Will the presentations be uploaded to their portal?
Yeah, I will upload them. If I didn't upload them until tomorrow, please just ask me on this, let's say, by email, and force me to do so, because of course I'm prepared to give you these presentations on the ePortal, but I need to prepare them in a way you will be able to see everything, because I had some animations on the slides, and some slides are covered by this final animation, so I need to prepare them for you to see all the information on the slide. Okay.
All right. Thanks.
Okay. I have a question also about the transmission through the fiber. And full duplex transmission through the fiber. Why it isn't just using circulator to separate uplink and downlink, not in WDM technique, but using one single fiber? So the reason is quite simple. I need to start up the presentation once more just to. Do you have any other questions connected with this test? If not, I will answer the question of Mr. Szymański. Okay, so yeah, you are proposing to. Okay, yeah, you are proposing to just make such a configuration. 1, 2, 3, and second circulator from the other side. 1, 3, 2.
I'm sorry, but you are not sharing, I think.
I switch off the sharing. Yeah, you should see right now.
Yes.
So we have such a structure. I think you think it can be done like this, yeah? So transmitter, receiver, transmitter, and receiver. But of course, if all elements are ideal, it is good solution. We can just transmit it in such a way, so it will be transmitted here, and of course from this transmitter to this receiver, so we'll have two waves propagating in opposite directions in a fiber. But unfortunately, we have also additional elements in such a network, some splices, some connectors. Especially in these cheap networks, we are using these PC connectors. They are making a lot of reflections. Yeah? And so look, if the distance for such a network will be, let's say, 30 kilometers, the received power can be comparable to the power which can be back reflected from this connector, for example, on the input to our fiber. Yeah? So you will have some crosstalk. This receiver will also receive some signals transmitted by this node of our network, and additionally it can receive also additional reflected signals, so it will receive a lot of noise because of these back reflections of every element in our fiber line. So this is why we don't use this duplex transmission in one single fiber at the same wavelength. You can of course avoid this problem if you have this receiver and transmitter at one wavelength and this one will be on the other wavelength. Yeah? And then you can make the receiver to be sensitive to the wavelength, yeah, to just receive only the signal at this certain wavelength. So in this case, this bidirectional transmission through one fiber will be possible and quite useful, in fact. Yeah, but if you want to make it on one wavelength for both directions, it will be not practical because of these back reflections and a lot of noise coming from these back reflections here.
Okay, so it's just that we are using not perfect elements. Right?
Yeah, of course, yeah, but because, you know, it is quite obvious. You can think you can transmit in these two directions, but yeah, in real life you will have a lot of back reflections in such a system. So they will produce you a lot of noise, and in fact, a lot of crosstalks also is possible.
Okay, thank you.
Okay, do you have any more questions regarding the test or regarding the lectures? Okay, if not, thanks for your attention. We'll see Monday on the last, not the last, but on the laboratory, yeah? Last before a test, and on Thursday on the test. So have a nice day and weekend, and see you Monday.
Goodbye.